Hello everyone. In this lecture, we will talk about the challenges for applying AI in Earth observation. We can think this both as challenges as well as opportunities. The same factors as we'll discuss through this lecture, we'll see they both presents themselves as a type of opportunity, and also in some way we can think them as the challenges that we need to address to apply artificial intelligence in the context of Earth observation. So the first challenge or the opportunity that we'll talk about is many applications. So what do we mean by many applications? Let us take some examples. So just think about the environmental monitoring. So this is one of the areas of Earth observation, right? So in the environmental monitoring, we can again think different application areas like forestry, urban area monitoring, vegetation monitoring, sea and rivers or marine monitoring, glaciers and ice monitoring, right? So when we think about each of these areas like forestry or urban area, as we'll discuss, we'll understand the appropriate data for each of these areas or each of the sub problems within these areas. That will be different, and not just the data, the appropriate architecture and other associated factors will also vary. So let us look into more details one of this particular area, that is forestry. So in the forestry, again, here I have identified some problems for our discussion, like species classification, deforestation detection, biomass detection, insect infection detection, right? So if you think about each of these problems again, like within the forestry itself, we'll understand that each of the problems poses different modeling challenges. And as I had already mentioned, that different inputs, different architectures in the terms of AI. So let us look a bit into one of this particular problem, let's say species classification. So species classification, if we are trying to model this problem, this itself, depending on how you model the problem, like what kind of assumptions you make about the problem can be quite different. Like let's say you assume that species are constant over a time period, okay? So if species are constant over a time period, then how many images would you use for the species classification for this given time period, right? Since species are constant, would it be just one image? However, let's say, okay, the species are constant over a particular month. Let's say, however, let's say there are like satellite image acquisitions every 5 days. So there are like approximate 5 to 6 images over this time period. So would you just say that, okay, that I don't want these 5 to 6 images, I'll just pick one image and just go for analyzing this one image? Or would you use all the 5 images? So here, I mean, there is no single answer, of course. if we have to answer this question, we'll also need to understand, like, let's say we are talking about multispectral images. So we need to understand that even if we have, like, let's say 5 or 6 images, not a single image might be, like, perfect. Like, there might be like clouds over particular regions in one image. There might be clouds over another region in the another image. So I'm considering that the region, the interregion that we are analyzing, that's quite large. So considering that, the cloud can be a factor, right? So cloud is not the only factor. There could be other factors as well. So it might make sense to actually use all the images. However, if you use all the images, will the architecture remain same as if you are using just one image? And again, if you are using all the images, even then, how will you fuse the outputs together to form a single output, right? At the end, your output is same, right? Because we are assuming that the species are constant over the time period, right? Over this particular time period. So how will you fuse these 5 to 6 images output to form a single output, right? So these are all challenges that we would face when modeling this problem. So there also the question arises whether it's a classification problem or a semantic segmentation problem. So let me clarify. In the context of this class, when we talk about classification, most of the times what we mean is that, let's say we have an image 224 cross 224 into a number of bands. So number of bands could be like 3 RGB image, could be 4 RGB NIR, could be, let's say, 13, like Sentinel-2 images of 13 bands, could be even in the hundreds, right? Let's say hyperspectral image. So that is fine. I'm talking more about the spatial size. So if it is 224 cross 224, let's say, in the case of the classification, what we are interested in is more to get a single label for the entire image. That is, let's say we will classify this image into one class, let's say building, let's say water, let's say airport. So this is classification, whereas when we say something as semantic segmentation, what we mean is that we are rather interested in getting one label for each pixel. So this can be, of course, in class semantic segmentation, but in many applications, it's actually binary semantic segmentation, where there is a class of your interest, let's say, that comes as the foreground, and the other classes comes as the background. So will this species classification, will this be classification or semantic segmentation, right? So this is also a question that we need to answer before we decide, okay, which type of architectures we are going to choose. So the problem becomes even more interesting. Let's say we had a species map from a while back. So we can probably make an assumption that, okay, like the species remains more or less constant and doesn't change so often. So that prior map could act as an additional input to our model, right? Or maybe we can, instead of modeling this as, instead of modeling this as a problem of just semantic segmentation, we could model this as a change detection problem. So on a similar line, if we talk about, let's say, deforestation detection, again, the question arises that how many images do we have? Do we have one image? Do we have two images? Do we have a time series image? The interesting thing about the deforestation detection is, if you think deeply, that these can be tackled as one image problem as well. Okay, maybe not that optimum, but it can be done. Maybe most of the literature, if you go back and like you search for the papers, you will find that most of the existing papers treated it as a change detection problems, so two images. However, you can also treat it as an image problem, that's a time series problem. And depending on that, maybe like if you are treating it as, let's say, a time series problem, let's say you are using LSTM. However, if you are, let's say, considering this as a change detection problem, maybe you are using a CNN-based Siamese network, or even deep change vector analysis. So the kind of architecture choice, this really varies depending on how you model the problem, right? Again, of course, the question, the same question that we had asked before, like deforestation, whether it's a classification or a segmentation problem, those questions remains, right? So similarly, whether it's like, okay, if we want to model it as a change detection, as I already discussed. So similarly, another problem from now slightly different area is the infrastructure monitoring, right? So infrastructure monitoring, under this itself, there are several problems, right? Like post-disaster monitoring urban sprawl or informal settlements, let's say. So we can even make, even more interesting problems like investment management of financial institutes, let's say. So financial institutes, let's say, they provide loans to construction companies. So they probably want to, monitor, like, okay, like the construction activities are actually going on for the places that they're interested in, right? So in that case, I mean, it's not, it's not just a matter of whether a building is there or not there. So in the case of investment management, it would be rather whether a construction activity is continuously going on. So a two-storied building last time, whether it's now three-storied or not, let's say, right? So that would need a different types of images. We need very high resolution data, let's say, and we'll need different kinds of architectures as well, right? So similarly, solar panels monitoring, right? Another problem of strong relevance today. Okay, so let us now move to our next challenge, which to some extent I think we have already started touching, right? The challenge that I'd like to talk about is that the Earth observation, we deal with many sensors, active sensors, passive sensors. They capture images with significantly different characteristics, right? So thinking about like just the multispectral passive sensors, even there is significant variation from one sensor to another sensor. So multispectral, hyperspectral, synthetic aperture radar, LiDAR. So these are just, like some popular sensors to name, and each of them, and inside each of them, like the multispectral, you could talk about Sentinel-2, Landsat 8, and all of them shows differences. You cannot just simply, train a model on one of these sensor and directly apply on data from another sensor without some sort of adaptation. There is differences with respect to spatial resolution. There is differences with respect to, let's say, spectral resolution. Even there is difference with respect to temporal resolution, which becomes important, let's say, when we are doing time series analysis. And in this scenario, different interesting questions comes in. Like, let's say, just think about this question. You have a few 3-band images and you do not have any, let's say, training data set. Okay, so I'm talking about like 3-band, let's say they are RGB images indeed. So you do not have any training data set, or maybe you have a very small training data set. Okay, so what can you do? If you think about this, one possible solution is that probably we can reuse a model which has been trained on ImageNet or a computer vision dataset, right? This will not be optimum, but however, this will give us still like quite fine result. However, let's say my 3-band combination, it was still 3-band images, but 3-band combination was significantly different from RGB, or the number of bands were not even 3 bands, right? Like, let's say we are talking about 13 bands or 100 bands in the hyperspectral images, right? So in that case, would we be still able to use the same solution of just using like a model trained on computer vision data set? Maybe no, right? So you need some kind of adaptation at least. The next challenge that I would like to talk about is in the context of the label. So this is like in the context of the label, there are multiple challenges that we'll talk about. This is the first one, that is many classes in the same scene. So in Earth observation images, very rarely we'll see like, okay, there is an image and this is just, let's say, building, nothing else. Most of the time, as you see in this particular image, there is building, also there is road, there are cars. So this is an example from a popular high resolution aerial image data set. However, if the resolution was lower, then of course in a particular scene there would be even more number of objects. So this brings us to the context that single image has many labels, and that is the reason semantic segmentation is preferred in the context of Earth observations. We have already discussed what semantic segmentation is, right? And this makes it clear that why semantic segmentation is more preferred. Or even like building on the top of semantic segmentation, other tasks like change detection and all. So on the similar note, another challenge is the ambiguity of the labels. So let us see an example. So the example that we see is from a mining area, and we see that manually annotating every pixel here is quite challenging, right? So this will need significant domain expertise. Why does it matter? It matters because think of if you had to create a data set, let's say for cat dog classification, or even something like, like building, road, semantic segmentation classification. You could pass this to volunteers, or let's say paid volunteers, or let's say through some engine dedicated for this, like Amazon Mechanical Turk, where untrained annotators could annotate them. However, for many practical Earth observation applications, this is not possible. Without expertise in the, or some level of experience in the specific area, this becomes quite challenging to annotate these images, which also means that for very specific applications, probably obtaining large scale data set is challenging. So this is what we discussed, right? That labeling may require extensive domain knowledge. So building on the top of this, the next challenge or opportunity, both I will say, is that sometimes weak labels are available, however they can be sparse and inaccurate. So weak labels, they come in different forms. Here we will be talking about one particular example, let's say OpenStreetMap. So OpenStreetMap you could use as a weak label. Let's say we are talking about building function classification. However, what happens is that this weak label sources like OpenStreetMap, I mean, this particular example is from a couple of years old. However, probably the percentage and all still will be still quite closer. And we see like even in cities from developed world, not all the buildings have been provided the corresponding function, right? Additionally, of course, there are additional challenges like OSM misalignment itself. It may not align well with the remote sensing images, which becomes more serious concern when we are talking about low resolution images. So the next opportunity or challenge, both again, is that in the Earth observation, we really have really large amount of data. So there are hundreds of satellites going around by different agencies. Of course, not all of them are like freely available. But even if we talk about freely available images, even then there is a plethora of data. Of course, at coarse of resolution. So data is collected, like let's say every 5th for some sensors, every, let's say, a 10th day for some other sensors. However, most of this data, of course, is unlabeled, right? So this provides us the motivation to explore the other learning paradigms in addition to the supervised learning, let's say semi-supervised learning or unsupervised self-supervised learning. So this big Earth observation data, as I already discussed, that this is continuously collected and low resolution data is freely available, but it's difficult to label, right? Why it's difficult to label, we have already discussed. The next challenge, again building on the top of this plethora of data that's available that we already mentioned, is how to use, multiple sensors and modality together, because the plethora of data, these are coming from different sensors, right? Different sensors from different space agencies, different companies at different resolution, different types of sensor. Okay. So using multi-sensor data for the same problem can be sometimes beneficial. Why? Because one sensor may complement the other. Okay. So the question arises, like let's say this optical and the SAR sensor, they complement each other, or there can be, like problem statements where you cannot really wait for both sensors. So think about, change detection in the disaster scenario, under disaster scenario like earthquake. Pre-change image, we can acquire using both optical and SAR sensor. However, once the event has occurred, we probably cannot wait for both optical and the SAR images. Probably the optical image, this is impacted by cloud, and we get a SAR image, we will like to then go for this optical SAR of pre-change and only SAR based post-change change detection, right? However, the question arises, can they be processed? Can the optical and the SAR sensors, can they be processed same weight sharing network? Maybe no, right? Even if we talk about just multispectral sensors, even then there is differences in the spatial and the temporal resolution or spectral characteristics, right? So there is also, like, in addition to the images, we can also bring in other kind of data sources, let's say tweets. So this is very relevant, let's say if we are trying to do building type classification. So if we have images, and let's say if we have geotag tweets, the tweets may serve as very useful information for the building type classification, right? However, this itself possesses several challenges. So one is in the same direction that we already discussed in the context of multi-sensor optical SAR, that can they be processed using not just weight sharing network. The question is, can they be processed even using similar type of architecture, right? So maybe you'd like to process one of them using CN and one of them using LSTM, right? Also, additional challenges are there, like geographic localization of non-Earth observation data like tweets. This can be often challenging, right? So in some cases, this is also very important to balance between the spatial and the spectral features. And this is very important, let's say, in the context of hyperspectral images. So depending on, like, given sensors like the spatial resolution and the number of bands, probably you would like to design the architecture in this way that, okay, the both characteristics are captured accordingly. So this is an example from the hyperspectral image classification. We often see, so this is not one particular architecture, rather we often see this generic kind of architecture in the case of hyperspectral image classification, where there is one branch of the architecture dedicated to model the spatial characteristics, whereas another branch of the architecture dedicated to model the spectral characteristics. So going back to the multi-sensor problem again, so we already thought about multi-sensor, let's say, in the context of change detection as well. However, let us take one step further. Let us think in the terms of time series analysis. So there can be, like, like abrupt changes. There can be gradual changes, like if the area that we are monitoring, this is a vegetation area, there can be gradual changes. And depending on the sensor's temporal resolution, maybe we would like to have, like, incorporate different sensors, right? So here, in this simple plot that we are showing here, the different colors, we mean different sensor. And we see that, okay, like since one sensor, if it covers your area of interest today, maybe it comes back after t number of days, and in between them, maybe if you want more acquisitions, you can use other sensors, right? However, this again brings us to the similar challenges that we discussed before, that how do we process these different sensors which might have different characteristics. Could we use same backbone for each of them? Maybe no, maybe yes, depending on how close those sensors are. Then how do we also capture the time series properties? So now a couple of challenges that I will discuss. And this again builds on the same context that we talked about, right? That sometimes we work with multi-sensor environment, right? Like we are training, let's say, model on a sensor. We are later applying this on another sensor. So this brings us to a problem like how to adapt to domains unseen during the training. So these domain differences, of course, this is not just induced by sensor differences only. It may be also induced by other reasons like season difference. It can be the case that the images are acquired in the summer season, but you want to apply the model trained on these images on in the winter season or some other season. Or let's say geography, right? Let's say the images were trained on a data set collected in Munich, and now you want to apply to Hong Kong. So there is like a significant geographic difference between them, right? Like let's say your task is, let's simplify this, let's say your task is just building detection, but even then the buildings in Munich will look significantly different from buildings in some parts of Asia, right? So on a similar line, another problem is understanding when the model may fail with unseen data, okay? This is again based on the same concept of domain difference. We can also define, so the similar chart that we saw before, we can also define them as the training data as in-domain data, and the test time, if there is a domain difference, we can consider this as out of distribution data. So we can potentially model this problem as out of distribution detection. Also, we can model this as domain adaptation, unsupervised domain adaptation, when let's say from the target domain we have some unlabeled data at least, or even as a domain generalization problem. So there are different problems depending on exact problem scenario that we are talking about. So thank you. We'll continue our discussion in the next lecture.